Welcome to the Aircraft Weight and Balance section of this class. In this lesson we will cover some of the terms used in and some of the federal aviation regulations governing aircraft weight and balance, as well as how to solve certain lever problems to aid us in understanding how to solve weight and balance calculations in later lessons. In this slide showing the Korean Air cargo aircraft sitting on its tail is one example of what can happen when an aircraft is loaded in an out-of-balance condition. Even while sitting on the ramp, an out-of-balance loaded aircraft can result in many thousands of dollars worth of damage, lost man-hours, and lost revenue. There are two important reasons for maintaining aircraft weight and balance control. The primary purpose is safety. An overloaded aircraft, when taking off, may not have sufficient power to clear obstacles at the end of the runway, such as trees, buildings, or rising terrain. An overloaded aircraft upon landing may experience significant damage to its undercarriage and landing gear. While in maneuvering flight, an overloaded aircraft may experience excessive structural loads, resulting in catastrophic failure. In an out-of-balance condition, where the aircraft exceeds its fore or aft limits, may result in a loss of control and a loss of the aircraft and its occupants. A secondary purpose of maintaining proper weight and balance is to achieve the utmost efficiency in flight. When an aircraft is flown in an out-of-balance condition, control surfaces are deflected to keep the center of gravity within its limits. This results in increased drag, lower airspeeds, and increased fuel burn. The empty weight and corresponding center of gravity of all civil aircraft must be determined at the time of certification. The manufacturer can weigh each airplane, or he may compute the weight and balance. The manufacturer is permitted to weigh one aircraft of every 10 produced. The other 9 are issued a computed weight and balance report based upon the averages of those aircraft weighed. Federal Aviation Regulations 135.185 require air carrier and air taxi aircraft to have a current empty weight and empty weight center of gravity established by an actual weighing of the aircraft within the preceding 36 calendar months. Privately owned and operated aircraft are typically only weighed when originally certified or after a major alteration that affects weight and balance. Weight and balance data can be obtained from the following sources: the aircraft specifications or type certificate data sheets, the aircraft operating limitations, the aircraft flight manual, or the aircraft weight and balance report. If the weight and balance records have been lost and cannot be duplicated, the aircraft must be reweighed. The datum is an imaginary vertical plane from which all horizontal measurements are taken for weight and balance purposes. The location of items such as equipment, fuel tanks, engines, seats, and baggage and cargo areas are given in inches from the datum and can be found in the aircraft specifications or type certificate data sheet. There is no fixed rule for the location of the datum. Each manufacturer is free to choose the location of the datum for their fleet. This slide shows some of the various datum locations utilized by different manufacturers for a variety of aircraft. The arm utilized in weight and balance calculations is the horizontal distance in inches that an item of equipment is located from the datum. A positive sign in front of the arm indicates a distance aft of or behind the datum, and a negative sign in front of the arm indicates a distance forward or in front of the datum. The moment, as used in weight and balance calculations, is a product of a weight multiplied by its arm, or moment equals weight times arm. The center of gravity of an aircraft is the point where the nose-heavy and tail-heavy moments would be in balance. As we begin thinking about solving weight and balance problems in aviation, it might be helpful to think about balancing the airplane like balancing a lever. Here we have a lever with two boxes, one sitting on either side of the fulcrum or balance point. This is the apex of the triangle, and we can think of it as the center of gravity of the airplane. In this example, we have one box weighing 10 pounds sitting 42 inches left of the fulcrum. How far would a second box weighing 25 pounds have to sit right of the fulcrum to balance the lever? If we think of the lever balance problems as a mathematical equation, we can draw it out with the equal sign sitting at the fulcrum. Remember that the moment of an item is its weight multiplied by its arm. In these lever problems, the moments on either side of the fulcrum must balance or equal each other. The weight of the box on the left side of the fulcrum, multiplied by its distance from the fulcrum, must equal the weight of the box on the right side multiplied by its distance from the fulcrum. So here we have 10 pounds times 42 inches on the left side, which must equal 25 pounds times an as yet unknown number of inches on the right side of the fulcrum. We can solve this algebraic expression by simply dividing both sides of this equation by 25. This will leave us with x on one side of the equation and the number of inches the box from the right hand side, or the blue box, must be from the fulcrum to balance this lever on the other side of the equation. As we can see here, the blue box, or the box on the right side of the fulcrum, must be 16.8 inches from the fulcrum for this lever to be balanced. In this lever problem, we again have two boxes on a lever, one on either side of the fulcrum. Except in this example, we know the distance each box is from the fulcrum and the weight of the box on the left. What we need to determine is how much the box on the right must weigh to balance the lever. If I want to find out how much the box on the right side of the fulcrum weighs, I need to remember that the moment on the left side of the fulcrum must equal the moment on the right side of the fulcrum. On the left side of the fulcrum, I have a moment of 16 pounds times 36 inches. On the right side of the fulcrum, I have a moment of x pounds times 48 inches. To solve this algebraic expression, if I divide both sides of this equation by 48, I'm then left with 16 pounds times 36 inches divided by 48 inches equals X pounds. 16 times 36 divided by 48 equals 12 pounds, and therefore the box on the right side of this fulcrum must weigh 12 pounds to balance this lever. In this example, we have two boxes placed to the left of the fulcrum. The first box weighs 20 pounds and sits 56 inches left of the fulcrum. The second box weighs 35 pounds and is placed 28 inches left of the fulcrum. Our task is to find out how much a third box sitting 36 inches to the right of the fulcrum must weigh to balance this lever. We will begin by writing an equation where the sum of the moments on the left side of the fulcrum must equal the moments on the right side. The moment of the green box is 20 pounds times 56 inches. We will add this to the moment of the red box, which is 35 pounds times 28 inches. The sum of these moments of the red and green boxes must equal the moment of the blue box, which is as yet undetermined number of pounds times 36 inches. Next, we will find the individual moments of the red and green boxes. 20 pounds times 56 inches gives a moment of 1,120 pounds for the green box, and 35 pounds times 28 inches gives a moment of 980 pounds for the red box. When we add these individual moments together, we get 1,120 inch-pounds plus 980 inch-pounds equals 2,100 inch-pounds. Now when we divide both sides of the equation by 36 inches, we discover that the blue box must weigh 58 1/3 pounds to balance this lever. What if we had a lever problem where the missing value was on the side of the fulcrum with two boxes? In this example, we have one box weighing 32 pounds, 20 inches right of the fulcrum. We have another box weighing 24 pounds, 12 inches to the left of the fulcrum, and a third box weighing 16 pounds, an unknown number of inches left of the fulcrum. We will begin again by writing an equation where the sum of the moments on the left side of the fulcrum must equal the moments on the right side of the fulcrum. This equation gives us the moment of the green box, which is 16 pounds multiplied by an as of yet unknown distance from the fulcrum, plus the moment of the red box, which is 24 pounds times 12 inches, its distance from the fulcrum. Those two moments must equal the moment of the blue box, which is 32 pounds times 20 inches, its distance from the fulcrum. Next, we will find the moment of the red box by multiplying 24 pounds times 12 inches to get 288 inch-pounds. Then we will find the moment of the blue box by multiplying 32 pounds times 20 inches to get 640 inch-pounds. Then in our next step, to getting x, or the unknown quantity, on one side of this equation by itself, we will subtract 288 inch-pounds from each side. This will leave us on the 11th side of our equation. 16 pounds times x equals 352 inch-pounds. Next, we simply divide both sides of our equation by 16 pounds. This leaves us x equals 22 inches, or the green box must be 22 inches left of the fulcrum for this lever to be balanced.